Black holes have long captured the imagination of scientists and the public alike, representing the ultimate extremes of gravity and the limits of our understanding of physics. Recent breakthroughs, however, are reshaping what we know about these enigmatic cosmic objects, and even what we imagine might be possible within their depths. At the intersection of advanced propulsion concepts, cutting-edge astronomical observation, and the relentless curiosity of theoretical physics, new questions are emerging, and some are beginning to find answers. Let's start with the tantalizing idea of escaping a black hole. Traditionally, the event horizon of a black hole is considered an absolute boundary. Once crossed, not even light can escape the gravitational pull. But in August 2024, theoretical physicists published research that pushes the boundaries of this concept. They explored what might happen if you could embed an advanced warp drive, a hypothetical propulsion system capable of bending space-time, within the outer region of a black hole. In science fiction, warp drives are often depicted as engines that can whisk a spaceship away at superluminal speeds by distorting the fabric of space around it. The new research, however, takes a more grounded approach, examining sublight, yet still extreme scenarios. By situating a warp drive just outside the event horizon, the study suggests, the negative energy required to sustain a warp bubble could be significantly reduced. This means maintaining a warp bubble, an energy structure that could, in theory, let a ship slip through the intense gravitational gradient of a black hole, might be more feasible than previously thought, at least in terms of energy demands. Perhaps most intriguingly, this arrangement could, under specific conditions, erase the boundary of the event horizon itself, at least from the perspective of the ship. In other words, the rules that make black holes one-way traps might be bent, or at least locally suspended, by the presence of a warp bubble. However, these theoretical possibilities come with significant caveats. The absorption of a warp drive by a black hole could decrease the black hole's mass and entropy, which raises deep questions about the laws of thermodynamics and the stability of such a configuration. For now, these remain theoretical exercises, but they ignite the imagination and push the debate forward about what's physically possible at the edge of a black hole. Now consider the possibility of not just escaping a black hole, but actually detecting the use of a warp drive somewhere in the galaxy. In June 2024, a new study addressed this very notion. Physicists asked, if an advanced civilization were using a warp drive, would we be able to spot it? The answer, it turns out, is both subtle and fascinating. A stable warp bubble, one that is not accelerating or collapsing, would not emit gravitational waves strong enough for us to detect. But that changes dramatically if the warp bubble were to accelerate, or if it were to collapse. In those situations, it would generate a distinctive signature of gravitational waves, ripples in the fabric of space-time. What's remarkable about these gravitational waves is that they would be unlike those generated by black hole mergers, neutron-star collisions, or other known cosmic events. Instead, they would carry a unique profile, potentially acting as a calling card for exotic propulsion. This opens the door for future gravitational wave observatories to search not just for natural phenomena, but for possible signs of advanced technology at work elsewhere in the cosmos. Turning to observational astronomy, the James Webb Space Telescope, JWST, has revolutionized our understanding of black holes and their environments. In July 2025, JWST's powerful infrared vision detected tidal disruption events in dusty, seemingly quiescent galaxies. These events occur when a star strays too close to a dormant black hole, only to be torn apart by tidal forces. Until recently, such events were thought to be rare, especially in galaxies where the black holes appeared inactive. But JWST's keen eye has uncovered that these cataclysmic encounters happen more often than anticipated, even in galaxies shrouded in dust that would have obscured them from telescopes operating at other wavelengths. This finding has profound implications. It means that black holes, even when dormant, are not as silent as we once believed. Instead, They occasionally awaken to devour stars, producing energetic outbursts that can be detected even across millions of light years. These observations are helping astronomers map the true population of black holes in the universe, including many that had previously gone unnoticed. JWST's contributions go even further. It has provided invaluable data on the origins of supermassive black holes, those enigmatic giants that reside at the hearts of galaxies and tip the scales at millions or billions of times the mass of our Sun. For decades, the formation of these cosmic behemoths has been a mystery. Did they grow slowly, accreting matter over cosmic time, or did they form rapidly in the early universe? By detecting the most distant black hole ever observed, JWST has offered compelling evidence that at least some supermassive black holes formed very early, perhaps less than 1 billion years after the Big Bang. This discovery supports the idea that the seeds of supermassive black holes were laid down quickly, possibly from the collapse of massive primordial stars or dense gas clouds. All these advancements underscore how the synergy of theoretical and observational science is driving forward our understanding of the cosmos. Theoretical physicists challenge our assumptions and sketch out what might be possible, sometimes even at the edge of a black hole. At the same time, observatories like JWST provide the hard data that grounds these theories in reality, revealing new phenomena and opening up questions that no one had even thought to ask. As for the true orbit of JWST itself, its carefully plotted path around the second Lagrange point, or L2, allows it to remain stable, cold, and shielded from the sun's glare. This unique vantage point, about 1.5 million kilometers from Earth, ensures that JWST can peer deep into the dusty hearts of galaxies and witness the dance of black holes and stars with unprecedented clarity. As we look to the future, the interplay between daring theoretical ideas, like warp drives and the possibility of escaping a black hole's grip, and the relentless pursuit of observational evidence promises to keep the field of astrophysics as vibrant and surprising as ever. Black holes, far from being the end of the story, may just be the beginning of discoveries that challenge everything we thought we knew about the universe and our place within it.